Okay, today we will start working on my old test 2. I think I used wrong solution notation here. My old test 2. And I will start from the most recent test 2 I gave from fall 20. And then after that, I go for spring 20th. And then spring 19. Remember spring 19 math 226, 260. That's from my West LA College class, and they have 6 tests. So your 4th test was divided into 6 tests instead, because they have daily class and each day only 1 hour 10 minutes. So I cannot give them 1.5 hour 2-hour tests. So with them, the test is shorter, but the shorter and less material for each test. Okay, now the way I code it this time will be as the following. Now please take a look that, for example, this, hold on, that's not what I want to do. Should be here. Okay, for this fall 20 Math 2 SMC test 2, today I will go over number 2 and number 3. So I hope when I post it on our discussion board later on, give me a second. So I plan to, later on when I post it on our discussion board, right? From the name, you can tell that, oh, you know what, that's spring, that's fall 20 Math 2 SMC test 2, number 2, number 3, like that. Okay, yeah, you know that after the test, I mean after the discussion, I post the notes actually here, right? Okay, now so hopefully by me numbering it that way, then just from the name you see clearly that, oh, that's from fall 20 Math 2 test 2, that's solution for number 2 and number 3, and so on and so forth. That's spring 20 Math 2 SMC solution for number 2, number 3. Okay, now for your test 2 later on, we would be able to do number 2 and number 3 up to now. And tomorrow's discussion, if you watch lesson 10 and lesson 11 from announcement 5, lesson 10 and lesson 11, lesson 10 and 11 from this announcement number 5, that will cover rational functions. Now, so once we are done with the material tomorrow, on Wednesday, we will go over question number 4, number 5 in this test, number 4 and number 5. Okay, and basically, once we're done with the rational functions tomorrow, then on Wednesday we will work on rational functions. Then on Thursday, I believe we will be working on inverse function, composition of function. Oh, hold on. We did composition of function in this class. So yeah, then on Monday next week, we will work on inverse function, composition of function. And I believe on Tuesday next week, we should be done with the material for test 2. Yeah. Oh, no. Actually, Thursday next week. Okay, but let's do what we can first. And today, basically, we'll cover the topics on polynomial, which we have finished last Tuesday, the discussion last Tuesday. Okay, now let's take a look on number 2. Let me write that here first. That will be the solution. I think I want to use blue color instead. Okay, let's see number 2. Yeah, there are 7 pages for this test, but that's because I give more space. Just like this is fall 20, right? So it's after pandemic. Okay, number 2, we have this polynomial. Now, it will be great if you can print out the blank test that I post on the discussion board so that you can follow me better here. Okay, number 1, we have that polynomial. use the Carter's rule of signs to find the possible number of positive real zeros. Positive real zeros depends on how many times the signs, how many variation of signs we have for the polynomial. So we see it only happens none here, one time here, another, oh no, this is none here, and another one here. So there are only 2 times, right? So the possible rational zeros, the possible positive real zeros, that will be either 2 or nothing positive zeros. Okay, the Scatter's rule signs for possible number of positive zeros depends on the variation of signs of that polynomial or that number subtracted by 2, by an even number. Okay, so suppose the variation of sign is 5, then the possible positive zeros are either 5 or 3 or only 1 positive real zeros. Okay, now then how about part B? Use the Scatter's rule of sign to find the possible number of negative real zeros or simply negative zeros. Then we take a look on P negative X. So replace X by negative X. And we will see the variation of signs, the number of variation of signs. Now, when you rewrite this, you notice that we actually have a skip. Degree of 2 suddenly constant, right? So later on when we do synthetic division, we need to be careful there. Let me fix it up. This will be negative 9x to the 5th plus 27x to the 4th plus x cubed minus 39x squared plus 4. Let's see the variation of signs. 1 time, nothing here, 1 time here, 1 time here. So there will be 3 or 1 negative zeros. Okay, and let's go on. Use rational zero theorem to determine possible rational zeros. The possible rational zeros, if it is a rational number, then it must be a factor of 4, in this case 1 to 4, over a factor of 9, which is 1, 3, 9. But don't leave it like that. You need to break it out. Okay, you basically need to spell out all possible rational zeros. So 1 over 1 plus minus 1 plus minus 2 over 1, 4 over 1, right? Okay, and then plus minus 1 over 3, plus minus 2 over 3, plus minus 4 over 3, plus minus 1 over 9, plus minus 2 over 9, plus minus 4 over 9. Okay, seems to be a lot though. There are 18 possible choices, but of course not all of them will be used, right? We know that according to fundamental theorem of algebra, we have only 5 zeros, right? We have only 5 zeros. Degree of 5 should have only 5 zeros. Now, next question, find the zeros of polynomial using the candidates you get in part C. Now, make sure you also mention the multiplicity of each zero at the end. Now, show only the work that gives you the zero. So in your test later on, make sure you have a scratch paper. You should have scratch paper all the time next to you, right? But this is where your scratch paper becomes very crucial because I want you to only show the work that gives you the 0. So px equals to, let me see, that's 9x to the 5th minus plus 27 minus 139 plus 27x to the 4th minus x cubed minus 39x squared plus 4. Okay, we will only show the work that gives us the 0. So assume my right-hand column here will be our scratch paper. Okay, my right-hand column here will be our scratch paper. And once I can find the zeros, then I copy that on the test paper, the one that gives me 0 only. Okay, now that's our polynomial. That's our polynomial, 9x to the 5th plus 27x to the 4th minus x cubed minus 39x squared plus 4. Now, let me tell you one little secret that may be useful most of the time, okay? It's the following, okay? The first thing I always check first, of course, you need to see the y-intercept. If the y-intercept is 0, 0, okay, means that's also an x-intercept, right? If the constant is 0, means we can factor x, right? Which means x equals 0 is a 0. You see what I mean? Then we can use that to reduce our polynomial to the lower degree. That's one. Second, next, if the sum of the coefficients is equal to 0, then x equals to 1 is a 0. Is a 0. Okay, now, and that's actually the case for this question also. Now, let's take a look. Let's take a look. Notice that when I add the coefficient, just imagine if I put P1, right? When I use P1, you will see that's 9, 1 to the 5th, which is 9, plus 27 times 1 to the 4th, which is 27, minus 1 minus 39 plus 4. Do you see that this is equals to 0? Right? Okay, now, so if x equals 1 is a 0, then x minus 1 is a factor. Is it right? Then we can use that syntactic division with 1 here. Okay, so 9, 27, negative 1, negative 39, 0, 4. Okay, remember we have a skip, right? From x squared, missing x, and suddenly just go to constant. So this is a placeholder. Okay, so I will divide by x minus 1, and the quotient we get here is basically the reduced part. We factor x minus 1 out, and we get that reduced part, which we will continue working on that. You see what I mean? Okay, now let's do that here. So going back to our test paper, okay, we know that 1 is a 0, right? So I will divide this polynomial by x minus 1. Okay, so knowing that 1 is a 0 is only half of the usefulness. The main purpose is because 1 is a 0, then x minus 1 is a factor. Okay, and that enables us to reduce the polynomial from degree of 5 to degree of 4. Okay, and we have the quotient here. That's what we will go on further from there. Okay. Now, so I go back to my scratch paper. One is a 0. Okay, and then from what we have on the left-hand side, we basically know that px is now equals to x minus 1 times 9x to the 4th plus 36x cubed plus 35x squared minus 4x minus 4. Is it right? Okay. Now we will be working on this as our quote-unquote new polynomial. Now take a look again. Does the sum of the coefficient is still 0? 9 plus 36 plus 35 plus minus 4 minus 4. That's a positive number. That's not 0. Right? So x equals to 1 is not another 0. You see what I mean? Well, basically 1 is a 0 with multiplicity of 1. It's not 2 because x minus 1 is not a factor for this. Okay. Now, on the other hand, we also notice something that from this polynomial here, we see that Q0 is negative 4, right? If you call that Qx, if we call this Qx, then Q0 is negative 4, yet Q1 is a positive number. You see that? Okay, so there by intermediate value theorem, there is a 0 between x equals to 0 and x equals to 1. You see what I mean? Yeah, imagine that the polynomial qx, right? Qx, Q0 is negative 4, but Q1 is positive. So there must be an x-intercept in between. Right? Okay, now then you look back to your candidates, which numbers, the rational numbers, that is between 0 and 1. 1/3, 2/3, 1/9, 2/9, 4/9. Is it right? Okay. Between 0 and 1, we have a 0 from intermediate value theorem. And from rational zero theorems, there are only 5 possible rational numbers in that interval 0 to 1 that can be zeros. Okay, so I will check those. So let me erase this to give me subset. Again, the right-hand side here is just our scratch paper. So let's try something between 0 and 1. Okay, but let me set up the syntactic division first. Let me try 2/3. Okay, I have 1/3, 2/3, 1/9, 2/9, 4/9. Okay, I will try 2/3 first. Why, Thomas? Actually, just random. I randomly pick this number. Okay, this is 9 times 2/3 divided by 3 is 3 times 2 is 6. 42. 42 divided by 3 is 14 times 2. 14 times 2 is 28. This will be 63 divided by 3, 21. 21 times 2 is 42. This is, is it right? Yeah, 42. This becomes 38. 38 divided by 3, around 10 times 2, around 20 something. This is 20 something. So when I add, this is a plus. Hold on. Hold on. So 2/3 is not a 0. Okay, but from here we have something important information from this synthetic division. Okay, we suspect earlier that between 0 and 1, there must be a 0, right? Okay, according to intermediate value theorem on x equals 0 and x equals to 1. Now, then in this interval 0 to 1, we have 1/3, we have 2/3, and then 1/9, 2/9, 4/9. Okay. Now, the thing is, from the synthetic division, when I did the synthetic division, it turns out that no more 0. It turns out that no more 0 to the right of 2/3. How do we know, Thomas? Now, you may want to take a look on boundedness theorem. It has something to do with boundedness theorem, which I didn't explicitly teach. But boundedness theorem says the following: if you do synthetic division on a positive x, so this is positive, right? If you do the synthetic division on positive x, and the last row are all positive number, if the last row is all positive number, it means there is no more 0 to the right of that. So 2/3 is not a 0, and anything over 2/3 also not a 0. So you'll notice that after we take that x equals to 1 out earlier, right? Okay, anything more than 2/3 is not a 0, will not be 0. So we can cancel +1, +2, +4, +4/3. You see what I mean? Okay. Now, this boundedness theorem will be useful to to cut your process actually by big time. Okay. Now, so we see that 2/3, when x equals to 2/3, we get a positive number, which means our 0 now must be between, earlier we say between 0 and 1, right? Earlier we say that we must have a 0 between 0 and 1, but after checking these 2/3, that gives us positive. Now we can update our interval instead of from 0 to 1, only from 0 to 2/3. Okay. Now, what I want to emphasize is this: even when you tried x equals to 2/3 as a 0 and it turns out it's not a 0, it doesn't mean you don't get any extra information from there. Okay. Sometimes you do things in our life, we do things in our life and we fail, right? And we need to do things differently all over again, right? But doesn't mean you cannot learn anything from that failure. Okay. Now, if you call this trying the 2/3, it turns out that it is not a 0. If you call that a failure, at least through this failure, we learn something that yes, there won't be any zeros greater than 2/3. And now I need to shrink my interval to search for zeros between 0 to 2/3. Okay, now between 0 to 2/3, is there any rational zeros that I can try? Then you look back into your rational zero theorem. Okay, you look back to your rational zero theorem and pick another number between between 0 and positive 2/3. Let me try, for example, 1/3. Okay, notice that I randomly pick this number. Okay, I randomly pick from the ones I mark in yellow here. Okay, I tried 2/3, this didn't work, right? Doesn't work. So either I try 1/3, 1/9, 2/9, 4/9, right? Okay. Now, and I choose to do 1/3. So 9 here divided by 3 is 3. This is 39 divided by 3, 13. This will be 48 divided by 3 is 16. Is it right? Yeah. So when I add, that's 12 divided by 3 is positive. Oh, that's 0 now. Okay, so 1/3 is a 0. Now, basically, then I continue from here. notice that what I have here is the same to this. Okay, now then I divide by x minus 1/3. I get that. Okay, so at this point, going back to our scratch paper, my px is equal to x minus 1, and I can factor this yellow part here now to be x minus 1/3 times 9x to the third plus 39x squared plus 48x plus 12. You see what I mean? And we can factor the 3 out. Do you see that? We have common factor 3. We have common factor 3 here now. We have common factor 3. Let me factor that 3 out. So if I factor 3 out, I get 3x cubed plus 13x squared plus 16x plus 4. Okay, now on the left-hand side, therefore, we can reduce by 3 multiplied by 1/3, right? Factor 3, maybe I say factor 3. Then it becomes 3, 13, 16, 4, right? Now, actually at this point, you can update your rational zero theorem. Consider that as a new polynomial that you need to factor further, right? Okay, now you see the variation of signs. There's no variation of signs. No more variation of signs there, which means there's no more zeros, on the positive, no more positive 0. And that's actually in line with the Scartas rule of sign that we have in part A. In part A, it says that we have 2 or 0 positive zeros, right? Okay, but we already got those 2. We already got those 2. We already get x equals to 1 and x equals to 1/3 as our positive zeros, right? Okay, and therefore we have no more remaining positive zeros. So the next time we do search for zeros, it has to be the negative one, the negative zeros. You see what I mean? Okay, now then let's see. Suppose we use a negative number to try for zeros. Okay, let's try -1. Let's try -1. 3 times -1 is -3. This is 10, -10. This is 6. This is -6. This is -2. So -1 is not a 0. -1 is not a 0. However, if you notice one thing, that when x equals to 0, for this blue one here, for x equals to 0, the y is 4. While when x equals to -1, the y is -2. Opposite signs, right? So there must be a 0 between -1 and 0. There must be a 0 between -1 and 0. And when we update our rational zero theorem from here, that's plus minus 1, 2, 4 over plus minus 1, 3. Okay, the 4 comes from here, and the 3 come from here. Okay, now that's the good thing about factoring 3 out. That's the good thing about factoring that 3 out. Okay, if I don't factor that 3 out, then at the bottom, I will still have 139. And on the top, I actually have a big number. Okay, 1, 2, 3, 4, 6, 12. Okay, so doing the common factor out actually reduce the possibilities of rational zeros for us to search. Okay. Now then, with those options that we have, can you guess another rational numbers, negative rational numbers between -1 and 0? Choose from here. We have either -1/3 or -2/3. It's either -1/3 or -2/3. Let me try -2/3. Okay, let me try -2/3. Why do you choose that, Thomas? I don't know. I just tried. Okay, 3, this is -2, this is +11. +11, that's -22 over 3, 48. So that's 26 over 3. That's -52 over 9. This will be negative. Okay, so let me write it down again. Between -1 and 0, we know there must be a 0 earlier because when we plug in -1, the output is negative. When we plug in x equals to 0, the output is 4. Okay. When we try -2/3, we get negative here. So we can update our interval that the 0 must be between -2/3 and 0. But if you look at this, right, if you look at that, if the 0 is a rational number, then it must be 1/3. That's 1/3 is the only rational number. -1/3 is the only rational number in this interval. Okay, so does it mean -1/3 must be a 0? No, no. It simply means if the 0 between -2/3 and 0 is a rational number, it must be -1/3. But if it is not rational, if it is an irrational, then it is not -1/3. Okay, now let me change that then. So I will change this to 1/3 later on. Okay, so a lot of trial and errors, a lot of trial and errors. Now those theorems that we learn enable us to shortcut here and there. If you know, the more you know the theorem, the more you can do. That's 12, this is -4, this is 12, this is -4, this is 0. So you see that -1/3 is a 0. -1/3 is a 0. And we still can factor 3 out here. Right? So we get 1, 4, 4. In fact, at this point, we can already write that this is basically x squared plus 4x plus 4, which is equal to x plus 2 squared. Right? Okay, so the zeros are x equals to 1 with multiplicity of 1, x equals to 1/3 with multiplicity of 1, right? Which x equals to 1, Thomas? The one here. This one here. It happens once. 1/3 is a 0. -1/3 also a 0. Right? Okay, 1 is a 0 with multiplicity of 1. 1/3 is a 0 with multiplicity of 1. X equals to -1/3 is a 0 with multiplicity of 1. And x equals to -2 is a 0 with multiplicity of 2. Why? Because x plus 2 squared is a factor. Okay, that associates to this. That associates to that. Okay, now then let's go on. Continue from there. It means if you want to write it in linear factor form, then px equals to, remember you factor 3 twice out, so it becomes 9. Okay, x minus 1, x minus 1/3, x plus 1/3, and x plus 2 squared. Okay, that's the linear factor of this polynomial. If we try to trace back, look back here, okay, if we try to look back, then once we factor x minus 1 out, then we get here x minus 1 times 9x to the 4th plus 36x cubed, blah, 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 from here. Okay, now then when we factor x minus 1/3 out, then we get x minus 1 times x minus 1/3 times 9x cubed plus 39x squared, blah, 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 from here. Now, when we factor 3 out, then we get 3 times x minus 1 times x minus 1/3 times 3x cubed plus 13x squared, blah, 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 from here. Now, then we have x plus 1/3 out, right? Times 3x squared, blah, 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 from here. When we factor another 3 out, when we factor this 3 out, so I get 3 times 3 times x minus 1, x minus 1/3, x plus 1/3 times x squared plus 4x plus 4, as you see here. Okay, now then when you factor that x squared plus 4x plus 4, okay, this guy becomes this. But what we had earlier here, it becomes here. You see? Okay, maybe I use different colors so that you can see it better. So what we had earlier here is what we have here. Okay, now so the last line that you see there, px equals to 9 times blah, 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 blah. Okay, that's the linear factor form. Okay, now let me erase the one in green so that you don't get confused. Yeah, I try to show you the relationship between what we had in between and what we had before. Okay, the one I write in green here is basically what the polynomial look like after you factor this, you factor that out. Okay, but if I leave it here, it seems like that's something you need to write in your test. But no, that's, I just try to connect that to why I have this at the end here. Why do I have this at the end? Okay. So Thomas, this one question is long, huh? Yes. In fact, the purpose we did number A, B, C is to prepare the stage for us to perform the actual computation in part D. Now, part E, use syntactic division to find P2, syntactic division to find P2. That's the polynomial, right? Going back to the original polynomial, 9, 27, -1, -39, the skip 0, 4, and P2. That's 9, 18. This is 45 times 2, that's 90. That's 89 times 2, 178. That's 139 times 2, that's 278. 278 times 2 will be 556. So this is 560. Now, but we are not done here. We need to explicitly say what is P2. This is 560. Okay, even though I use syntactic division, okay, but the underlying concepts I use here is actually remainder theorem. To find P2, one way is to use syntactic division. right? Another one is you plug 2 in. So you plug 2 in there, you'll get 9 2 to the 5th plus 27 times 2 to the 4th, so on and so forth, right? But trust me, it will take you some time to actually compute it that way. And here I specifically say I want you to use synthetic division. Okay, so the answer for this question is P2 equals to 560. Okay. Let me erase the one in yellow so that you don't get confused. Oops. Oh, I end up erasing too much. Put it back. This is 9. So that's the solution. Okay, and then for part D, the solutions are this. This is the solution. Okay. Now then, part F, determine the far-end behavior of the polynomial. Far-end behavior of a polynomial only depends on the leading term. The leading coefficient is positive, the degree is odd, so the far-end behavior will be bottom top. Or if you don't remember that term that you use, you can just use this like that. So which means if you go very far to the left, you go to the negative infinity. If you go very far to the right, the graph will go to positive infinity. Now part G, sketch the graph. Sketch the graph. Now label the x-intercept and the y-intercept. Okay, be aware with the multiplicity. You don't need to graph that to scale. Let me lasso this so that we can erase that faster. So again, the one I marked in green only on for my scratch paper earlier. Now suppose I need to sketch this now. Okay, my y-intercept is 0, 4. X-intercept are 1/3, 0, 1, 0, negative 1/3, 0, and negative 2 with multiplicity of 2. Okay, now we know the far end behavior is negative infinity on the left-hand side and positive infinity on the right-hand side. Now let's fill up the gap in between. Now negative 2 is a 0 with multiplicity of 2, so it will behave like an x squared in at that critical number. Okay, degree of 2, multiplicity of 2, it won't change sign, right? Okay, it will just touch, it will not cross the x-axis. And then x equals to negative 1/3 is a 0 with multiplicity of 1, so it will cross that just like usual. It will cross that. All of the rest of the zeros are multiplicity of 1, so it will cross that just like usual, like that maybe. Now remember, because the graph is not drawn to scale, then you need to label the x-intercepts and the y-intercepts. Okay, put that negative 1/3, put that negative 2. If you try to graph this to scale, the graph will look very, very different from this. Okay, either it becomes very, let me show you. If you try to graph this to scale, okay, now what happens is if you try to graph it to scale, then you will actually lose a lot of important characteristic of this function. So y equals to 9, let me show you the y equals to the graphing paper, 9x to the 5th, and then plus what? I forgot. Plus, let me see, 27x to the 4th. 27x to the 4th minus x cubed minus 39x squared plus 4. Now that's what it will look like. Okay, if you try to draw it to scale, right? Okay, then it is possible you end up with a lot of just like, so imagine if your window is only like this, then you will not see the full picture of that. If you try to zoom it too far away, you won't see the details. If you zoom it too close, right, you will not see the bigger picture, right? So there's a balance between to have, for you to see all the characteristics, all the x-intercept and y-intercept, we cannot draw it to scale. Basically, that's what I'm trying to say. Okay, and when you try to draw it to scale, then you may not see the general shape of the graph. Okay, what we need only, you show me the x-intercept and y-intercept and how the functions actually behave in the surrounding area. And still, we still have the far end behavior, you know, and so on and so forth. Okay, so do not use graphing calculator or graphing software for this, because once you start doing that, your graph will be very distorted. Okay, it looks very strange. And this is degree of 5 though. Okay, so it's not that high. The one we will see next, I believe, is degree of 6 or maybe degree of 7. Okay, and the graph will be a lot more, it must be worse. Yeah, it must be worse. Okay, now I spent a lot of time for this one question here because today we will basically do a lot of such questions. Okay, we'll do a lot of such questions. Now, students who watch this recording, I hope you don't skip, oh, I know this part, and then you jump to number 3. Oh, I know this part, and you will lose a lot of details. Okay, because for this number 2, I give you a lot of details. For our number 3 next, okay, I will just remind you a little bit here, a little bit there of what we did earlier. Okay, now number 3. We have this px equals to 7x to the 7 minus 16x to the 5th plus 75x cubed minus 108x. That's degree of 7. That's degree of 7. Let me enlarge this a bit more so that you can see. That's degree of 7. Means we should get 7 zeros. Okay, let's see. Use the Carter's rule of science to find possible number of positive real zeros. So there's 1 here, another 1 here, another 1 here. So there are 3 or 1 positive zeros. Now, how about part B? If we want to find possible number of negative zeros, we need to first observe. Oh, I should use the blue color. Red color is kind of like the scratch work that I apply on the paper. You still can see that on your, if I work it out myself, then you will see that. If I use green color, then that's basically purely on your scratch paper. Okay, so this is 3 or 1 positive zeros. I don't want to write too much such that you get overwhelmed. But if I write too little, you may wonder where I get those numbers from too. Okay, when p negative x, basically replacing x by negative x, right? Okay, now you will see if they have odd exponent, the sign will change. If they have even exponent, the sign will not change. Now the thing is, all the exponents we have here are odd. Okay, are odd. In fact, you will see that this is actually equals to, in this case, happens that if you factor the negative out, you will get px inside, right? This implies this function is actually an odd function. This function is an odd function. It must have origin symmetry. Now, that's a big help. That's a very big help. Okay? That's a big help. This is has origin symmetry. Not always though, in this case only. Okay, now let's see how many negative zeros we're supposed to have. You will see, because it has origin symmetry, then what happened on the right hand side will be basically replicated on the left hand side upside down. Okay, now let's see if we really do that. And you see that, say, change one time, another one time, another one time. Right? Okay, so it has 3 or 1 negative zeros. And now use rational zero theorems to determine the possible rational zeros of Px. Note that you need to factor an x out first. You see that Px has common factor x, right? Okay. Has common factor x. So I will factor x out. So I get x times x to the 6 minus 16x to the 4th plus 75x squared minus 108. Okay, now then from there, what's the rational zero theorem? C will be, of course, 0 is a 0, right? Because we factor that x out. Okay, but beside that, you will have plus minus the factor of 108 over the factor of that 1. The factor of 108 over the factor of 1. Oops, not that one. So the factor of this one here. Okay, which is only 1. Now the factor of 108, however, there are a lot, right? 1, 2, 3, 4, I believe 6 is 1 times 108, 2 times 54, 3 times 20. If I divide by 3, it'll be 36. Divide by 4, that's 27. Divided by 6, that's 18. Divided by 8, so there are a lot, huh? Let me do it this way. 1 times 108, 2 times 54, 3 times 27, 4 times, no, not 27, is it right? 3 times 36, 4 times 27, 6 times 18. Is it right? Yeah, 6 times 18. How about not 8 times, it's 9 times 12. I think that's only, no. Yeah, only those. So you will see when I write it in this pair, okay, then the order, if you want to list the factors from smallest to the highest, that will be going this way. Okay, now it depends on how your arithmetic teacher teach you to find the factors of a number though. Okay, so after 6 is 9, and then 12, 18, 27, 36, 54, 108. Okay, now let me list them out. That will be C equals to 0, plus minus 1, plus minus 2, plus minus 4, plus minus 3, plus minus 4, plus minus 6, plus minus 9, plus minus 12, plus minus 18, plus minus 27, plus minus 36, plus minus 54, plus minus 108. Okay, those are the list of all possible zeros, possible rational zeros. Now, number D, what we need to do is then to find all those zeros. Find all those zeros. Okay, now my right hand side will be again my scratch paper so that you see how I think. Okay, our polynomial is, we already factored the x out, right? So we get x to the 6, maybe I write it here. So px equals to x times x to the 6 minus 16x to the 4th plus 75x squared minus 108. And don't forget, this polynomial is an odd function. The original polynomial is an odd function, which means if you can find a 0 which is positive, then the opposite of that number is also a 0. Well, because it has origin symmetry, right? If it has origin symmetry or y-axis symmetry, then a 0 on the right must be a 0 on the left. You see? Right? If this function is an odd function, right? Then if this is a 0, this must also be a 0. Right? If this is 3, then this is negative 3, like that. Okay? Origin symmetry, right? Now, let's work on this. When I observe the sum of the coefficients here, 1 minus 16 plus 75 minus 108, I get a negative number. So when x equals to 0, that's negative. When x equals to 1, that's also negative. So it doesn't mean there's no 0 in between. Okay, but because they have the same sign, there is a small chance there's a 0 in between. Not to say that if you take a look on the list here, all the positive numbers, all the positive rational zeros, you don't have anything between 0 to 1. Okay, so we will check something greater than 1. Okay, we'll check something greater than 1. Let's see, what will that number be? Let me check 3 or 4. Why not 2, Thomas? You can try. I mean, just do something. Okay, just do something. So x to the 6, 0x to the 5th, negative 16x to the 4th, 0x cubed, 75x squared, 0x minus 108. Okay, I will not try 1 because when I tried that earlier, I just add the coefficients. It doesn't give me 0. So let me try, let's say 3 or 4. Let's try 3. Hey, it works. Lucky us. So 3 is a 0. Okay, 3 is a 0. Nice. Nice. So 1, 0, negative 16, 0, 75, 0, negative 108. The nice thing about in this case is that because 3 is a 0 and we know that's an odd function, so negative 3 later on must also be a 0. But Thomas, why didn't you try x equals to 2? You can try. I was thinking this way. When I try 3, if it doesn't work, I may be able to single out 2. Okay, but I just try to do something instead of just staring at that question, not doing nothing, right? Doing a lot of what if does not solve your problem. I mean, in real life too, you know. Okay, so what I did is actually doing something. Okay. Now, because I know that's an odd function, I try right away negative 3 also. I know it will work because this is an odd function. It should be 0. Okay. Now, actually, at this point, you can update your guess. You can update your guessing because this polynomial basically x to the 4th minus 7x squared plus 12. You see? Okay. So if you update your rational zero theorem, it will be just plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12. Knowing that 3 and negative 3 is a zeros, all of a sudden you reduce the polynomial such that these guys in your list suddenly disappear. Why? Because if you take a look on the rational zero theorem for this updated polynomial, right? Now, you have a new list of rational zero theorem, new list of rational rational zeros through rational zero theorem. Okay. Now then from here, you can try again. Can I try x equals to 2, Thomas? Go try. I mean, we never know. We never know. Okay. We never know. Should I try 1? No, because we tried earlier with the original polynomial. It didn't work. So it won't work anyway right now. Right? Okay. So this is 1, 0, negative 7, 0, 12. And then let's try 2. Okay, we try 2. 1, 2, 2, 4, negative 3, negative 6, negative 6, negative 3. I'm sorry, this is negative 6. Negative 6, this is negative 12. Oh, see? 2 is a 0. Right? Okay, 2 is a 0. And again, because 2 is a 0, then negative 2 must also be a 0, right? Negative 2 must also be a 0. Because it's an odd function, remember? Okay, now at this point, we already have degree of 2. We already have degree of 2, and that is actually x squared minus 0x minus 3. So we get x squared equals to 3, x equals to plus minus square root of 3. So the zeros are x equals to 0, don't forget that one, x equals to 3, x equals to negative 3, x equals to 2, x equals to negative 2, x equals to square root of 3, x equals to negative square root of 3, all with multiplicity of 1. Okay, now before I go to the next part, before I go to part E, let me make you be aware of something else. Now, some of you may realize that when we take x minus 3 and x plus 3 out, once we factor these, once we factor x minus 3 and x plus 3 out, this guy here looks like that, and it is actually a quadratic-like expression. It is a quadratic-like expression, okay, which we may be able to factor. Maybe we are able to factor without going through syntactic division. Okay, so for example, like once you are here, right, then you just say, oh, this is actually x squared minus 3 and x squared minus 4. Okay, set it equals to 0, right? Because you are looking for zeros, then you will get x squared minus 3 equals to 0, x squared minus 4 equals to 0. So x equals to plus minus square root of 3, x equals to plus minus square root of 4, which is 2. Instead of doing this. Now, I'm not saying that this is more elegant. No, that's just an alternative way to do that. Okay, that's just an alternative way to do that. Okay, now one big warning, please, please, please do not use photomath to factor this. You will see photomath will be able to factor this, but the work will be so messy and so unreasonable. I will just basically ask you how you get this. How do you get that? You know, in other words, students who use photomath to do this problem, will not be able to do A, B, C, N, E, N, F. But all of the sudden, they can do part D and G if you use photomath. Okay, so let me give you this big warning. Okay, even if I allow you to use photomath such that you depend on photomath, okay, photomath will not be able to answer other questions except part D and G. And photomath will give you that answer without any reason that you can understand or study from for that part D. Okay, so trust me, don't use photomath. It doesn't bring you anywhere. Okay, yeah. I honestly did that last year when we first changed to remote learning. I knew some students actually using photomath, right? I warned them, don't do that. But I know during the test, they use photomath. I just let them go. Fine, you know, let's see how far you can go. And none of those students who use photomath in their tests actually survive even test 2. Some of them still, how to say that they just don't know that they're so bad that they still continue with their test 3. It's just disaster. It's just disaster. It's like, if you want to give me easy grading, go for it. You know, you will see that they are all empty tests. Okay, easy grading for me. But that's not why I'm here. That's why I'm telling you, don't do that. You want to learn something, you never learn from cheating. Okay, you never learn from technology that makes you don't need to do anything. Okay, that's not what technology for. Okay, now part E, continue. I'm about to give you a break, don't worry. Use syntactic division to find P4. That's 1, 0, negative 16, 0, 75, 0, 1, minus 108. Don't forget, we still have 0 for the constant. Okay, degree of 7, 6, 5, 4, 3, 2, 1, constant. Okay, and then I will find P4, so 4. We expect this to be a very big number. Am I doing it right? 1, yeah, 2, 4, 16. This is 300. This is 1200. This is 4,368. So P4 is 4,368. How about the far end behavior? The leading coefficient is positive. The exponent is odd. So it will be again bottom top. Or something looks like that. Okay. By the way, formally speaking, the far end behavior supposed to be denoted this way. Supposed to be this one. Limit x going to positive infinity of px is, the right hand behavior is infinity and left hand behavior is negative infinity. That's what it means to be far end behavior. The right end and left end behavior. Okay, but I try to avoid using limit notation as much as possible in this class. Now sketch the graph below, label the x-intercepts and y-intercept. Do not need to sketch that to scale. Oh, I'm sorry. Now, then again, the nice thing is that's an odd function, right? That's an odd function. So the x-intercept are 0, 0. What else? 3 and -3. And then 2 and -2. And then, is it radical 3? Yeah, radical 3 and negative radical 3. All of them with multiplicity of 1. So it will cross the x-axis all the time. Yeah, approximately like that. Yeah, the last part is not nice though. Just leave it like that. I try it again. Yeah, approximately like that. Okay, now let's see what happens if you use, well, let's see what happens if you use graphing calculator. That's x to the 7th, right? And then what? Minus what to the 5th? I forgot. Let me see. Minus 16x to the 5th. 16x to the 5th. And then what, x cubed? 75x cubed minus 108x. What am I doing? Okay, give me a second. So this is minus 16x to the 5th plus 75x cubed minus 108x. See, that's what it looks like. Okay. Now it's as if you don't see the x-intercept and y-intercept here. Do you realize that? If you zoom it too much out, then you will see only lines. It's not clear, right? If you zoom it way too in, then you don't see, you may see the x-intercepts, but you don't see the y-intercept anymore because it's way too close to the y-axis. So graphing it using graphing calculator or graphing softwares will show you what the graph look like, okay, but not complete. Yeah, it won't be a complete graph. Okay, you need to have a very big screen to be able to see this. Okay, and don't forget, remember what is P for? Remember what is P for? If we look back to our paper earlier, our P4 is positive 4,000 something. Okay, so while 3 is a 0, 4 is a very positive number. So you know the graph will be very distorted. Okay, if you try to graph it to scale. Okay, now right now it's 10:46. Let me give ourselves a break and then we go on with spring 20th. Yeah, spring 20, number 2 and number 3. Okay, see you later. Here, let's take a break. Okay, let's do it faster this time. For the first 2 questions, I put a lot of explanation. Now, much less explanation. Okay, because we already remember, recall from the first 2 questions, what is the Descartes law sign, for example. Now, positive real zeros change only 2 times. So 2 or 0 positive zeros. Oh, I need to use blue. Okay, for the negative real zero, let's take a look p negative x. If the exponent is odd, I change the sign. If the exponent is even, I keep the sign. So the sign change 1, 2, 3 times. So there will be 3 or 1 negative 0. Okay, now use rational zero theorems to determine the possible rational zeros. So C will be plus minus the factors of 49, 1, 7, 49. Yeah, 49 is 7 squared, right? So the factors must be a factor of 7 or power of 7. And denominator 2, so I mean the leading coefficient is 2, so denominator must be a factor of 2. So C will be plus minus 1, plus minus 7, plus minus 49, plus minus 1/2, plus minus 7/2, plus minus 49/2. No other possible rational zeros but this. Okay, now I hope from me going over my old tests, you see that even if you are repeating this class, if nobody ever put everything together, those from 3.1 to 3.3, everything, or 3.4, everything together, like I do here, it is impossible for you to actually cheat. Just like, oh, you know what? I have Thomas' old tests with the solution. I can just do it. I can just study during the test. No, it's impossible because you will run out of time. You will definitely run out of time. Okay. Now, polynomial, let me write down the polynomial again down here. That's 2x to the 5th plus 3x to the 4th minus 98x cubed minus 148x squared plus 49. Let me make sure. 148x 49, that's 98x 2, 3. Okay, so that's the polynomial. Okay, and then the right hand side here it will be my scratch paper, right? 2x to the 5th plus 3x to the 4th minus 98x cubed minus 148x squared plus 0x plus 49. Okay, P0 is 49. How about P1? P1 is 2 plus 3 minus 98 minus 148 plus 49. That's a negative number, right? So there must be a 0 between 0 and 1. Okay, what negative number, what rational number between 0 and 1? Because according to rational zero theorem, there must be a 0 between 0 and 1. Okay, that will be what? 1/2, right? Okay, let's try 1/2. 2, 3, negative 98, negative 148, 0, 49. Let's try 1/2. This is negative 192 divided by 2, negative 98. Is it right? No, 96, my bad. No, 90, this is 196, this is 98, this is negative 49, 0. So 1/2 is a 0. One half is a 0, and let me do this first. And 1/2 is a 0, and notice that inside the third row here is all even numbers. So let me factor 2 out. So now I get 1, 2, negative 46, negative 98, negative 49. Should I try 1/2 again, just in case it's multiplicity of 2? No, you don't need to. Why? Take a look on the rational zero theorem right now. Right? Okay, if you take a look on the rational zero theorem, the numerator will be either 1, 7, 49, but the denominator, it's only 1. There's no other way. So you don't need to try 1/2 because it won't work anymore. Okay, either you try 1, but we tried 1 earlier, it doesn't work, right? So let's try 7. Okay, let's try 7. So 1, 7, 9, 63, is it 15? That's 105. That's 7. See, so 7 works. Okay, now according to our Descartes rule of sign, we have only at most two positive zeros, and we get those twos already, 1/2 and 7. So we should stop searching for zeros on the right-hand side. And we can see that also here, that there's no more zeros to the right-hand side of 7 according to Descartes rule of sign. Okay, now let's look back. Then we will be dealing with now, let me erase this. So I basically, on my scratch paper, I go to the next page, let's say, okay, and then I try, okay, 1, 9, 15, 7. Let me try -1. Let me try -1. And actually you will see -1 will work if -1 is a 0 if the sum of the alternating terms are equal. The sum of alternating terms are equal. That's something new, huh? If you add the coefficients and it is equals to 0, then 1 is a 0. If the sum of the alternating terms are equal, then -1 is a 0. Okay, you will try. Let's see. Let's see. Here, then you get -1. This is 8, -8. This is 7. It's -7, 0. Right? Okay. If the sum of the coefficients of alternating terms are equal, then -1 is a 0. Okay, let me just continue directly from here. -1. Okay, but this is already degree of 2 though. I'm sorry, this is +1 here. So this is degree of 2. This is 2x, x squared plus 8x plus 7, which factor to be x plus 7. x plus 1. Okay, so the zeros are x equals to 1/2, x equals to 7, x equals to -1, x equals to -7. Actually, x equals to -1 is a zero with multiplicity of 2. It happens once here. It happens once here. And notice that the sum of the alternating terms are equal. You see that here? Right? 1 plus 7 equals to 8. Right? Okay. So the rest of zeros are multiplicity of 1. This is multiplicity of 1. That's multiplicity of 1, except x equals to -1. Okay, now let's continue with part E. Part E, find p -2 using syntactic division. So that's 2, 3, -98, -148, 0, 49. You know, most students on that during these tests, in the actual test, when the actual students took this test, most of them actually forget this 0. They don't realize there is a skip there. So most of them actually stuck here. They get stuck in part D. They cannot go on because of what? Because of that place value. Okay, the placeholder. You need to be aware of that though. Okay, be aware with that placeholder. Okay, that little mistake make that those students actually lose at least 10 points. Okay, -2. 2, -2, that's -4, -1 times 2, that's 2, -96 becomes positive 192, that will be 44, is it right? 44, times -2, that's -88, that's 176, so this is 225. So P -2 is 225. Determine the far end behavior of Px. Either you say bottom top, or you say you sketch the far end behavior this way, or you say limit x going to infinity of Px is infinity. Limit x going to -infinity of Px is -infinity. Okay, now then go on, part G. Now the y-intercept for this function is very high, 49. So again, if you try to graph that to scale, you won't be able to accommodate all of them. X equals to 1/2, x equals to 7, x equals to -1, multiplicity of 2, and what else? -7 with multiplicity of 1. So the graph will be bottom top, right? Okay, at -7, multiplicity of 1 means it crossed the x-axis. At -1, it's multiplicity of 2, so it bounds. At 1/2, it's multiplicity of 1. At 7, it's multiplicity of 1. So approximately it looks like this. Okay, that's for this number 2. See, I did this in how many minutes? 15 minutes? I hope I'm not going too fast. Let me know if you think I'm going too fast, right? I already slowed down at the beginning to kind of like put things together, review everything together, and put it into this one questions, right? But we already know by this point that what is the Scatter-Short sign, rational zero theorems, okay, and how to find the zeros, how to do the syntactic division, for and behavior, and put them together into the sketch of the graph. This is for number 2. Let's go on with number 3. This is x to the 6. Let me enlarge this a little bit more. That's x to the 6. Okay, find this, use the Scatter-Short sign to find the possible number of positive real zeros. There's no change of sign I see here. There's no change of sign. So there will be no positive zeros. Okay, how about on the negative side? That's x to the 6 minus 9x to the 5th plus 31x to the 4th minus 51x cubed plus 40x squared minus 12x. How many times it changed? 1, 2, 3, 4, 5. Huh? Only 5. So 5 or 3 or 1 negative 0. No positive 0, but at most 5 negative zeros. Oh, we have common factor x, huh? Yeah, we have common factor x. So factor that x out first. So px is now equals to x times x to the 5th plus 9x to the 4th plus 31x cubed plus 51x squared plus 40x plus 12. Now, 0 is not a positive, it's not a negative number. Okay, so according to rational zero theorem, C will be 0 or plus minus the factor of 12 over the factor of 1. Is it right? Yeah, the leading coefficient is 1. Oh, okay, so over factor of 1. So the possible rational zeros are 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12. Okay, now we know 0 is a 0. Hold on. Earlier, did I mention that? Okay. Yes, I need to mention 0 is a 0 though. Okay, so px equals to x times x to the 5th plus 9x to the 4th plus 31x cubed plus 51x squared plus 40 plus 12. Remember that we don't have positive zeros. Okay, now according to rational zero theorems, I still include the positive zeros here. But when I actually try it later on, I don't need to try any positive one because according to the Scatter-Short sign, none of them will be positive. Okay, so I will work on the negative zeros. Is it okay? I will work on negative zeros. But which negative zero should I try? Let me check this one thing first. When I add the alternating terms, are they equal? The coefficients of alternating terms, are they equal? The one in yellow, that will be 1 plus 31 plus 40, that's 72. The one in blue, that's 9 plus 51 plus 12. Is it 72 also? Yeah, that's 72 also. Now, when I say alternating terms, means the sum of the odd exponents, the sum of the coefficients of odd exponents with the sum of the coefficients of even exponent should be the same. Okay, that's what I meant. Okay, from there we see, oh, they are the same, right? Both of them 72. So negative 1 must be a 0. Did I copy anything wrong? Oh, here. Yeah, this is should be. 23. I did it twice. Okay, and you can do it again. Let's try again. So the sum of the alternating terms here, that's 24, 36. The sum of the alternating terms here is also 36. Oh, so one is just a negative one is just another zero for this. So -1 now is a 0 with multiplicity of 2. Let's check that again, just in case it happens again. 17, is it equals to 19? No, so no, -1 is not a 0 anymore. -1 is not a 0 anymore. What other number would you like to try? Let's just try it directly here. Would you like to try 2, maybe? -2, I mean. Let's try. It works. Lucky us. I did that by guessing though. It's -1 doesn't work. So we have only -2, -3, -4, -6, -12 to try, right? Okay, remember the rational zero theorem, right? Okay, there's no other choices. Okay, then let's see. But at this point, then we have x squared plus 5x plus 6. That's x plus 2, x plus 3. Okay, so the zeros are x equals to -1 with multiplicity of 2, right? -1 with multiplicity of 2. And then x equals to -2 with multiplicity of 2 again. Why? One from here, another one from here. Okay, and then x equals to -3 with multiplicity of 1. How many zeros we have so far? We have 5 zeros, right? We have total of 5 zeros. But as I remember, our degree is degree of 6. Oh, the other 0 is 0. Okay. So x equals to 0 is also 0 with multiplicity of 1. Okay, don't forget that part. Don't forget that part. Because we factor that here, right? Remember we factor that here. Maybe I mark it in green so that you remember that. Okay, now then let's go on. Part E. Use syntactic division to find P2. So 1, 9, 31, 51, 40, 12. Don't forget the 0. Oh man, this will be big. $314, 354 times 2, 708, 720, that's 1440. So P2 is 1440. How about for n behavior of Px? Leading coefficient x to the 6, even degree, leading coefficient is positive, so it must be top. Okay, so it will look like this. Or we can say as x goes to positive or negative infinity, Px will go to infinity. Okay, that's just another limit notation. In fact, that's the limit notation our textbook is using. Now sketch the graph. Yeah, it's nice that we have degree of, this is degree of 5. The nice thing here is that this question is on easy side because what? It's degree of 6, right? But we get one of the zeros, x equals to 0. That's easy. Okay, and -1 is a 0 twice. Only multiplicity of 2. So together with x equals to 0 with this, right, we have only degree of 3. All you need is to find one of the zeros such that it becomes degree of 2 that it's easy for us to kill. Right? Okay, now then the x-intercepts are x equals to 0, 0, 0. The zeros are -1 and -2, -3. It's top, is it right? It's top. Okay, so -3 is a 0 with multiplicity of 1, so it cross. -2 is a 0 with multiplicity of 2. -1 is a 0 with multiplicity of 2. It's too sharp there, sorry. So this is -2, this is -1, this is origin. That's the sketch of the graph approximately. Okay, what number is this? Number 3. Oh, number 2 we are done, huh? Yeah, number 4 is already a rational function. If I have time later on, I go over some questions from rational function, which we can do easily already. Okay, now let's see number 6 from spring 19, test 2, number 6. This is the one I told you that we have 6 tests. So part of their test 2 are their test 2, spring 19 test 2 for us associated to our part of our test 1 or part of our test 2. Okay, now that's why later on you see that I will go over their test 3, right? Spring 19 test 3 is part of our test 2, but also part of their test, our test 3. Okay, but most of their test 3 is actually in our test 2. Okay, now if you think about this, we actually went over a lot of problems from this question here. Yeah, but we will only do number 6. Okay, we can do more though. We can do more, but I will just leave it other time. Okay, number 6. We have px equals to -2 x plus 2 squared, x minus 1, x minus 2. What is the y-intercept? Oh, find what is p0. P0 is -2 times 2 squared times -1 times -2. That's -2 times 4 times -1 times -2. That's -16, huh? Oh yeah, -16. So 0, comma, -16. How about the x-intercept? Oh, you can get the zeros already. So x-intercepts are -2, comma 0, 1, comma 0, 2, comma 0. -2, comma zeros, right? Because -2 is a 0, right? 1 is a 0, and 1 is a real number. 2 is a 0, and 2 is a real number. How about the far end behavior? What is the degree? What is the degree? This is px equals to -2 times. Now, if you think about this, you get x squared, x and x from there. So you will get 2x to the 4th something. Is it right? Now, then the far end behavior will be bottom. Or or it will later on when you sketch the graph, it will look like this. Okay. When you go very far to the left, it goes to negative infinity. When you go very far to the right, it goes to negative infinity. How about the sign graph of Px? How about the sign graph of Px? The zeros are negative 2, 1, 2. Those are the zeros, right? And I believe negative 2 is a zero with multiplicity of 2. I'm sorry, this should be 1 here. That should be 1. That's not 0. That's 1 there. It should be 1 here. Right? The zeros are negative 2, 1, 2. Now, the thing is, we already compute the y-intercept earlier. We get negative 16. So when x equals to 0, we get negative, right? These are the 0, this is 0, this is 0. Now 2 is a 0 with multiplicity of 2. Negative 2 is a 0 with multiplicity of 2. So there's no change of sign here, change of sign here, change of sign here. Okay, that's the sign graph. Now, when you do sign graph, do not forget the zeros, the critical numbers. Okay, the critical numbers. Is it a critical number that gives you zeros, or is it a critical number that gives you undefined? Now, that's for this one question here. I think I can do composition of function already. So there are some questions from this test and the previous test 2 that has composition of function. But I will do it later, okay, if we have time. Let's do this Spring 19 Math 260 test 3 first. And that's the solution. Now we have this polynomial. Use the Scarta's rule of signs to find the possible number of positive real zeros. 1 times change, 2 times change, so 2 or 0 positive zeros. We get so used to it. I hope you can do it so fast also. Why do I use red? I should use blue. Red is my scratch pen, ink. Okay, part B. Use the Scarta's rule of signs to find the possible number of negative zeros. So I need to find p negative x first. That is negative 2x to the 5th plus 3x to the 4th plus 33x cubed minus 59x squared minus 51x plus 36. How many times the sign change? 1, 2, 3. So there are 3 or 1 negative zeros. Part C, use rational zero theorem to determine possible rational zeros. So C will be plus minus a factor of 36. Dang, that's a lot. 1, 2, 3, 4, 6 times 6, 36. So that's 4 times 9, 3 times 12, 2 times 18, 1 times 36. Over 1 or 2. So the possible rational zeros will be plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 9, plus minus 12, plus minus 18, plus minus 36, plus minus 1/2. 2/2 is 1. We already have that. Plus minus 3/2, plus minus 9/2. And that's all. Okay. 18/2 is 9, right? So I don't need to list that anymore. Okay, let me copy the px down here. So 2, 3, negative 33. Probability polynomial 2x to the 5th plus 3x to the 4th minus 33x cubed minus 59x squared plus 51x plus 36. I hope I don't write anything wrong. Okay, now let me add the coefficient first. 2 plus 3 minus 33 minus 59 plus 51 plus 36. Do I get 0? This is 41, that's 92, positive 92 minus 92. So yes, that's 0, right? So 0, I'm sorry, 1 is a 0. 1 is a 0. Because 1 is a 0, then I use synthetic division to reduce that to be degree of 4. Okay, now when I add the coefficients again, I think that's negative, huh? Yeah, when I add the coefficients again, that's negative. How about when so because I add the coefficients is negative, so the so 1 is not another 0. On the other hand, when I add the alternating terms, do they have the same sum? I don't think so. Yeah, when I add the alternating terms, I don't get the same sum. Oh, okay. So what can I do? So negative 1 is not a 0. Yeah, negative 1 is not a 0. And what should I do from here, Thomas? I don't know. Just do something. Okay, staring at that will not help, right? So let me try. I will just use a blue pen, by the way. If it doesn't work, I will delete, I will erase them. Okay, if it doesn't work, I will erase them. So let me try 2. Will 2 work? 2. No, it doesn't. No. Should I try 3 or 4? Maybe I try 4. I try 4. This is 52, so that's 24. That's 96. Is it right? Yeah, that's 96. That's 9, 36. Oh, yeah, 4 works. 4 works. Will 4 work again? No, will not work anymore because there are only 2 positive zeros and we get both of them already, right? On the other hand, we remember if the coefficients are all positive, there's no change of sign here, right? So there's no more positive 0 for this polynomial. Will negative 1 work? We tried negative 1 earlier, it didn't work. But you can try that now. If you add the alternating coefficients, do you get the same number? No, they don't, right? We don't. So negative 1 will not work. Negative 1 will not work. And I will not try positive anymore. Let's try negative 2. No, negative 2 doesn't work. Negative 2 doesn't work. Try negative 3 then. How do we know, Thomas, which one to try? We don't know. Just do something, dude. Okay, sitting down, doing nothing, staring at that will not help. Okay, the thing is, like, we have degree of 5, so we already get 2 zeros. You just need to get another one, because once you get another one, this is degree of 2 now, right? Okay, that's a degree of 2 now. We get already 3 zeros now. Oh, negative 2, negative 3 is a 0. Good. Then this is 2x squared plus 7x plus 3, which I expect you to be able to factor. Okay, so we get x equals to the zeros are x equals to negative 1/2. All of them with multiplicity. Oh, no. X equals to negative 1/2, x equals to 1, x equals to 4. All this with multiplicity of 1. And x equals to negative 3 with multiplicity of 2. Because it happens here and here. Okay, now then the next question, write px in factored form. Notice that x equals to negative 1/2, x equals to 1, x equals to 4, all of them with multiplicity of 1. And x equals to negative 3 is a 0 with multiplicity of 2. Right? Okay, now then the polynomial must be, always start with the leading coefficient 2 times x plus 1/2, x minus 1, x minus 4. Okay, those are for all the multiplicity of 1, and this is from the leading coefficient. Okay, and then finally, x plus 3 squared because of multiplicity of 2. Okay. Let me write it again. So x equals to negative 1/2 is a 0, x equals to 1 is a 0, x equals to 4 is a 0, all of them with multiplicity of 1, and x equals to, what's that? Negative 3 with multiplicity of 2. Right? So the linear factor form will be 2 times. The leading coefficient has to come out. And the ones inside the parentheses has to be x plus or x minus something only. Not 2x plus 1. No. What is the y-intercept? The y-intercept is 0.36. How do you know that? Just look at the polynomial. When x equals to 0, the constant is 36. Right? When x equals to 0, then P0 is 36. Okay, how about the x-intercept? So the x-intercept is negative 1/2, 0, 1, 0, 4, 0, negative 3, 0. Use synthetic division for P, negative 2. Oh, we have done that many times. 2, negative 3, positive 3, negative 33, negative 59, positive 51, positive 36. I need negative 2 here. That's negative 58. So P negative 2 is negative 58. Determine the far end behavior. Leading coefficient is positive. Leading coefficient is positive 2, which is positive, and the degree is 5, which is odd. So it must be bottom top. I'll sketch the graph below. X-intercepts are 1, 0, 4, 0, y-intercept 0, 36, and the other x-intercept -1/2, 0, -3, 0 with multiplicity of 2. Let me put it on the top. So the far end behavior is bottom top. -3 is a 0 with multiplicity of 2, so it will bounce. The rest are multiplicity of 1. And they actually give us a hint that when x equals to -2, the y is -56, 58. This is -2, -58. Remember that? Okay, just to add extra details. But that's basically it for this polynomial. So you see that the first two questions we spend more than 1 hour, right? Or 1 hour, 10 minutes. Okay, but then since then, in the last 50 minutes, we already did 3 problems with these full complete polynomials first, plus a little problem from here. Plus a little problem from this number 6 here. Okay, so it's really about how well prepared you are, and how you are able to put all those theorems, all those rules together later on. Okay, now with the time I have left, let's do a little bit of maybe this question. At Spring 19 Math 260 Test 2. We can answer the question of the domain and the composition of function. Yeah, inverse function is something we will do in our class next week. Okay, I mean, in lesson 12 or lesson 13, we already have that. I think lesson 12 already have that. Now, let's see here. What is the domain of this function fx? X cannot be -4, right? That should be an easy question. So the domain will be all real numbers except -4, or -infinity to -4 union -4 to infinity. Okay, now I will skip the inverse function until later. Okay, how about G compose fx? What is the gx again? G compose fx means G of f of x. Now G fx is equal to what? X minus 3, x plus 4. So x minus 3, x plus 4. Now, what is G blah? G blah is blah plus 2 over blah minus 5. G blah is x plus 2 over x minus 5. Okay, so G of that will be x minus 3 over x plus 4 plus 2 big over x minus 3 over x plus 4 minus 5. Okay, G blah is blah plus 2, blah minus 5, blah plus 2, blah minus 5. Okay. Now then let me multiply by the LCD to clean up and simplify. So x plus 4 on the top, x plus 4 at the bottom, such that we get x minus 3 plus 2 times x plus 4, x minus 3 minus 5 times x plus 4. So that will be x minus 3 plus 2x plus 8 over x minus 3 minus 5x minus 20. That will be 3x plus 5 over negative 4x minus 23. Now that's the composition of function. So what is the domain of this composition of function? I believe that's the next question. Yeah, what is the domain of G compose F? That will be all real numbers except, let's copy that down first, except what? What number are we supposed to avoid here? Negative 23 over 4, right? You see that negative 4x minus 23 cannot be 0, right? So x cannot be negative 23 over 4. Okay, so all real number except negative 23 over 4. But there's one more things we need to be aware of. The domain of this compositional function also needs to exclude those numbers that you do not take in for f. In other words, you need to avoid negative 4. Yeah, negative 4 cannot even go into f. Then it cannot be the input of G compose F. Is it okay? Now, last question. I think after this, I will take off. Okay, what is G compose F of compose G of X? But this is actually the same to G of F of G of X. Right now, but notice that we already done with G compose F in part D. In part D, G compose F is, in part D, give us, what's that? 3x plus 5, negative 4x minus 23. I copied that up there. G of f of x is 3x plus 5. Is it right? 3x plus 5? And then negative 4x minus 23 over negative 4x minus 23. Is it right? Okay. Now then you basically replace the x there by gx. Okay. So this will be 3 times, what is gx? What is gx? 3 times x plus 2. Maybe I write it this way first so that I can see better. This is 3 times g plus 5 over negative 4g minus 23. Okay. Okay. G f blah is 3 blah plus 5 over negative 4 blah minus 23. Now, if you replace that blah by g, then we get 3g plus 5 over negative 4g minus 23. But our g is an ugly guy, x plus 2, x minus 5. Okay, now then from there, we will clean up again, right? Multiply by the LCD x minus 5. then we get 3 times x plus 2 plus 5 times x minus 5 over negative 4 times x plus 2 minus 23 times x minus 5. That will be 3x plus 6 plus 5x minus 25 over negative 4x minus 8 minus 23x plus 115. That will be 8x minus 19 over negative 27x plus 107. Okay, of course, you can also do this from the very beginning, right? G going into F, and then after that go into G. Yeah, you can also do it that way, but it will take too long though. Okay, this is where I will end. See you on Wednesday. Tomorrow with our Tuesday, Thursday class, we will continue with rational functions. I don't think I can finish the whole rational functions, but with the lecture, lesson 11, that I assume you will watch in advance, then we must be able to do all of that 3.5, okay, rational functions. So that on Wednesday, we will be able to continue with number 4, 5 from fall 20, test 2, number 4, 5 from spring 20, test 2, and then number 3, number 4 from spring 19, test 3. Okay? Yeah, so please make sure that you watch that lesson 11 and 12. I think that lesson 11, I'm sorry, lesson 10 and 11 for rational functions, okay, such that on Wednesday, we can do at least 6 questions from here. Okay, see you then.